Well, let's continue with tonight. This one is called Evolving Network Technologies, and some of them probably have already evolved. They're not evolving, or I guess that may be evolving. Everything's kind of evolving all the time, but talk about network convergence and expanding the use of IP networks. We're expanding IP networks continuously. It's one of the reasons we ran out of IP addresses and had to go to IPv6, which was the plan all along. It just when we had to do it, and running out of addresses kind of forced that a little earlier. Virtual networks and cloud services. We'll talk about cloud services. I'm going to walk through a virtual machine and the configuration and the things that can be configured, what it does. You've seen it a couple of times when we do those things, but those devices are there. So Module A is network convergence, the unified communication systems, industrial control systems, and I think somebody said that they worked in those, so they can help us out here. The industrial control systems are being brought into the IP world. They had their own protocols for a long time, and they probably were safer having their own protocols. But now they're in the IP world. Well, they're compromisable when we do those things. Storage area networks, and then quality of service mechanisms. We're not going to configure quality of service. We've talked about, we try to look at where it is and the kinds of things that we can do, what we're doing with quality of service, what the heck is it, why do we want to do it when we are managing the network. So convergence. So the role of networks is expanding, and it is more and more and more use of networks and more use of networks, data networks. We have a lot of social networks, and they're expanding too, and being used for different purposes, different methods. And just back to what we're doing tonight, what we're doing in this course, the role of networks. The network is expanding because just not very long ago, we wouldn't be able to do this. In the past, many networks did coexist separately. You couldn't bring them together. We might have an analog network and a digital network. They were using different protocols. Not that many years ago, we had NetWare, which used its own protocol, IPX. And Microsoft used its own protocol, IP, and it used its own version of IP. Which wasn't necessarily the standard version. So back to everybody tried to be proprietary for a long time. So these things didn't necessarily work together. But technology, specialized can be expensive. And regulations, legal requirements sometimes prevented the separation that we want to, force the separation of these things. But what we want to do here, convergence, is when we're bringing these things together. And what the image up here is supposed to be showing is we're bringing voice and data and video together in one network. And we do that. You do that all the time. You may have a voice over IP phone at home, a voice, phone modem, or a phone capability in your router. You stream video and you send data across it. So we do those things. But in this one, we're talking about the PSTN, the publicly switched telephone network, the old voice analog network, dial-up with it, where we used a modem in order to get across the network. And the two computer types, generally different networks. I've talked about NetWare and Microsoft. We throw Apple in there too because they had their own protocol, AppleTalk, to communicate among their devices. So we got the Microsoft networks over here, we got the NetWare networks, and we've got the Apple networks. So what we want to do is to bring all of those together, and then TCP/IP networks are or have, and I think probably have, I'm pretty sure that most people aren't using the NetWare protocols. They may be using the NetWare software, but they converted to IP somewhere around 2005. So their IP, AppleTalk, I don't know if anybody's using it. AppleTalk was pretty slow. And if you ever see somebody that shows you half of an IPv4 address, that's what an Apple address used to look like. So TCP/IP networks have done that, and this is where we combine the voice, data, media, and we're now putting industrial controls in this thing too, and data storage down at the bottom. I want to try to demo a data storage. You don't have to watch me stumble through it. It's already set up. I just want to show you the elements to do data storage using the network, and we can do that to have distant storage someplace. Why we want to do that? It makes backups easier because we don't have individual machines. We have a centralized storage array. The problem with that is that if the storage array fails, then we've lost an awful lot of capability. We've lost the storage with it. But converged networks, and this is a definition, a network convergence refers to the coexistence of three networks within a single network: video transmission, a telephone network, data communications. Priority packet setting will be used in a converged network, as there needs to be priorities put in place so that the packets containing data for a voice transmission, not mitten, will take priority over the packets from someone who's just browsing the internet. So quality of service is what that's saying, the priority of the packets. That we assign certain data, certain packets, a higher priority than other ones. So we're not having an equal access network. We're assigning priorities to some things, and then the next one is probably going to be is video would get the next higher priority. The reason that we want voice is because we like to have clear telephone calls, and if you don't have clear telephone calls, you're going to hear about it when we do these things. And this is just the image over here, just a network that has all of those different elements, I think, in it. We've got mobile devices over there, data repositories, desktop applications, sensors and devices, web services, and then the gateway up here, the engine, the data repositories in these things. So we have all of those different devices. Voice over IP is pretty popular. We started using voice over IP quite a few years ago, and this was one that, in the scheme of things, in the prioritization of things, we dedicated a certain amount of we had a T1 line at the time, a certain amount of the T1 line to voice, so that it never failed. At least we hoped it never failed. They are very small packets. It's digitized, very small packets. We're talking about sizes in Ks, and they're not going to, each one of them is not going to be authenticated, or not going to be acknowledged. It's not going to be a TCP, it's going to be a UDP. And this was kind of the goal down at the bottom. The real-time service was the goal of UDP all along. We have digitized voice here sent over the lines. Our ears tend to be analog, so if we drop a couple of packets, we're probably going to fix that with our analog ears and things like that. So the voice, 2 or more directions. The more directions, if we have a conference call, we're going to have more than 2 individuals on it, but 2 generally is what it's going to be. And the support phone, we have related services with it. I was going to drag this over here just to show that, yep, we can do that. If you wanted to do, and we're going to talk about some other things that are necessary in order to put one of these calls onto the publicly switched telephone network. But if you want to use it within your network, all you need is routers. And if we look at these routers here, and I probably can't, we can look at, and it probably won't make a lot of sense, but maybe some sense. If we look at it, this is the network, the default router, and the option 150 here, what we're going on, IP DHCP pool. It's a DHCP server. When we get down here, ePhone, device security none, the MAC address, and then the type 7960, the button 11. It's going to get an IP address, and it's going to get a phone number, IP source address, auto assign. It is, I know it looks really confusing now, but that's not a lot of lines of configuration to do these things. And when we do them, this one is 1, 2, 3, 4, so I'm going to use this one because I can't read this one's number. 1. And then we can go over here and answer that one. So we can do these things, connect it, and if I just started it up, it would tell me that it was doing IP configurations for these things. But different things, different evolving technologies. This one is has evolved. I think it's actually in use in a lot of places. And I don't know, maybe there, maybe not, maybe where you work, maybe not. But a lot of people are using it because we don't have to do the phone bills anymore. We have control of what goes on the system itself, or at least we sort of have control of what goes on with the system itself. I'm going to have, I think, need to look here. Yeah, an image here that's got all of the elements, but we'll look at some of the key definitions for this. Voice over IP, VoIP, protocol optimized for transmission of voice data, telephone calls. VoIP gateways, a voice over IP gateway converts the voice and fax calls between the PSTN, publicly switched telephone network, POTS, plain old telephone system, and your IP network, the big public phone system that we use. Sampling, audio is converted from an analog signal to a digital signal through a technique known as sampling. And then a codec, compress, as they say, a special algorithm called a codec, compress VoIP data to reduce bandwidth consumption. And on the receiving end, the same algorithm is used again to decompress the data. And you probably may have had that happen. I have sometimes. You try to play something and it won't play because you don't have the codec that it was compressed with. So you can't decompress it and watch it, video, song, or whatever else with those things. Latency, how long it takes. Latency, sometimes called delay. Too much latency causes the callers to talk over each other because you're waiting, and then, okay, I'll say something, and then both of you are talking at the same time. Jitter is the thing that gets you. It says that a variation in the delay. What it is an inconsistent delay, or inconsistent delay or latency. That, one of them has a microsecond, the next one's got 2 microseconds. So as a result, the voice stream is not smooth. And you get pauses, jumps, jitters, choppiness. You sound like Alvin and the Chipmunks sometimes when you have those things. Unified communications, appliances that plug into the network and provide a variety of communication services, voice, voicemail, instant messaging, and faxing. So we're not providing just voice communication. We're providing all the other services that go along with it. And this is kind of what it would look like. Is an IP network uses its own devices and protocols, connects phones rather than computers. And we have, let's go around this thing. We have the gateway here connects the PBX to the outside network, to the PSTN. So we have a gateway that gets us out, and gateways, that's what gateways typically do. The default gateway gets us out of our network onto the internet. So the gateway gets us out of our voice network onto the telephone network, the PSTN, the public telephone. Additional services, we have an application server. The additional services, voicemail, and those sorts of things are going to be there. Maybe the messaging softwares would be there. The phones themselves, the handset connects to an Ethernet switch. And these are typically going to be PoE, power over Ethernet switches, because we can send the power to the phone and we don't have to have a power supply for it. Usually external power supplies. We don't have to have the power supply for it, and we don't have to find a plug to plug it in. So PoE switches typically are going to be used for VoIP phones. The call agent replaces the logical functions of the phone exchange, responds to the local phones, routes the remote phone calls, and then the MCU, the multi-control unit, is going to manage the conference calls if we have those. And the workstation over here, the workstations, Cisco at least, has a lightweight phone that can be run from a workstation, or you can have the full-blown hand set with these things. So the devices, the support devices that you might see in a VoIP network when we use those things. The protocols, the signaling protocols, these are to set up, tear down the calls. You have to set up to do the dialing, and then to do the hang up when we're done to break the connection. H3.323 is mature protocol, mirrors the traditional phone session. SIP, and I think SIP is the one, that's the one that Cisco uses predominantly. The Session Initiation Protocol is replacing the H323. Open, extensible, with variations between vendors, and you're going to find that consistently that there's going to be some variations. Each of them is going to tweak their particular version of the protocol in their own way. The Media Gateway Control Protocol, an IETF standard based on the client-server model, and then the Skinny Client Control Protocol, SCCP, Skinny, Cisco proprietary. It has custom features with the Cisco devices. Cisco tends to be, as long as you stay within a Cisco world, all of their stuff works well, and all of their stuff works, pretty well automatically. These things will find their own configuration information. Once we've configured the switch, and you saw, they'll get their own IP address. They'll get their phone number based upon the MAC address. And then we'll use a power over Ethernet switch, a PoE switch, and we don't even have to find an outlet for the phone itself. So this is one of those little things that we go down the clickies here, and it shows the connection. So Alice is calling Bob. We have the VoIP server here that she's going to connect to, and the VoIP server on the other network that the call is going to go from one to the other. So we're going to go through the WAN to get there. PSTN, the VoIP server, we have to have a gateway to get out onto the publicly switched, the PSTN network. And then here, extension, username, password, whatever we're going to use with these things. They have number ID, caller ID, all sorts of information available on these. Whether the user is available or not, if you get ready to call them, and they can set as not available, or whatever else, or call later. Lots of different capabilities with these things. A VoIP trunk on the internet, if we're going to go across the internet for these things. The different versions, I said the machine, a soft phone on a computer, or a hard phone, an actual physical phone. An old analog phone here through a VoIP converter. The interesting thing here, we talk about this in fax. Fax machines are analog. You actually have to have a converter, a fax converter, to be able to use your digital line, to use your fax machine on the digital line to do these things. So the different ones, the VoIP gateway, PSTN, the WAN, we got the trunk, the VoIP trunk, and then we could call locally within our network by just using the extension numbers that are available to us. The protocols, and I guess more protocols, I got that other one stuck in the middle there. A real-time transport protocol. So we're not using TCP, or in this sense it has its own protocols, video and audio usage. Secure real-time transport protocol. Are going to add encryption to them, and then the codecs again is going to convert the analog audio into the compressed digital, and then we have to have the same codec at the other end in order to be able to listen to it. Streaming media, same type of operation as the VoIP, except it's one way. It's going to be simpler since it's one way. We're going to broadcast it And we're kind of sort of doing that here, streaming one way, but you can talk and we could share. I could give you the make you a presenter and you could share. So it could sort of be two-way, but generally it is a one-way video with a couple two-way audio and then the chat that's available to us. Quality of service, and I think we've seen some of this, but what we do is assign each of these their own priority. And voice is typically going to be the highest priority, so that we want the phone calls to be clear. So this one's going to be the highest. Video and interactive is going to be 2, and then kind of whatever's left over. Best effort service here is going to be the data. And best effort, before we do QoS, quality of service, everything is best effort, which means that nobody has any advantage over anybody else. So we have the ability to prioritize these things. This is going to be in the data packets. And I guess that maybe let's try to look at where that's going to be in the data packets. Let me start a Wireshark here. And maybe start a Wireshark here. It says it's starting, but maybe not. Yeah, I've got 2 of them. So if we open one of these things, let's open TCP here. If I go into, try to make this a little bigger because we can look at it down here. Let's go down here and look at that's a hang up, we don't want that. I think that there is and you see this is just for a few seconds, just when I talk about how much traffic goes on these things. When we go to the IP, the header here, this differentiated services field is where the markings are going to be. This is a CS0, which is basically no priority. And we're going to have, I think I've got a table that you see some of these codes. Each of the codes, this is where the code goes to tell the data, to tell the devices, the routers and the switches, which of these things have a priority. This is not a tagged frame. If it was, we could have a layer 2 priority in here also when we do those things. So we're going to be able to prioritize the data based on what it is. Voice starts out on the switch because the phones connect to the switches and they automatically get a higher priority from the switch. And then we have to configure the rest of the devices to trust those markings. To say, yep, this is a voice packet, let it go. This is the carpool lane, let them go. They're not going to have to get into the congestion of rush hour. They're going to get in the carpool lane and go there. Video and interactive, going to have a priority that's going to be a little bit less than voice, and then our best effort, no priority at all, is going to be the data. When these things get configured, they should be configured so that the best effort actually gets some time. You don't want to set a system up so that the voice and video gets so much priority that data doesn't get anywhere, that it gets totally stopped. So we need to be able to do those things. This is just another image for what we're going to do with these things. We got the before and the after down here, and I think this is the one out of the book. Special applications, the voice, they kind of jump around and go higher and lower into each area. And down here in the after we do the assign the priorities, each of them gets the portion that they should have all of the time. And the one at the top, same sort of thing here. What we're doing, we're doing audio traffic, priority queue, video. It's going to have its own And then the data down at the bottom, the best effort queue, is going to be as available, bandwidth on an as available basis when we do this, when we have that. Two different ways to do these things, or a number of different ways to do these things, but a couple of things that are going to happen here, a couple of ways to do this in terms that you may need to know. Policing and shaping. Policing drops packets in the incoming and outgoing directions. Out of profile packets are dropped. So it just simply hacks them off, drops them, doesn't send them anywhere. It depends upon TCP to say, hey, didn't get here, send it again. Causes the TCP retransmits. Shaping, and what we're not going to get in this is jitter and delay. Shaping, outgoing only. If something happens, we go above the allowable, what it does is buffers the data until there's enough bandwidth to send that data. So we get delay here. We can get delay, and we can also get jitter with these things. This says marking and remarking is not supported. In policing, one of the things that can happen with the priority that the packet can be remarked to a lower priority, so it will go into a different queue, a different line in order to be sent. But traffic policing drops some traffic shaping. It's going to buffer. We get delay with shaping. We don't get delay with policing. So the classifications, the kind of what we've talked about, and we get another policing and shaping image down here, but the best effort, default. There are no priorities. Everything is on an equal footing. Everything gets the same options, or the same, it's a level playing field. Latency-based, higher priority traffic is delivered first. And the latency-based, the higher priority traffic here is going to be voice. Reliability-based, and what kind of classification? Reliability-based, delay is more acceptable than dropping. So in that case, we're probably going to want to look at shaping for those. Undesired, the lower than the best effort, and then we have a lower priority. What this is showing up here, the guaranteed bandwidth and the burst bandwidth that we may have, and then when we get into the red area, the traffic's going to be dropped. That would be in the policing. If this happened in a shaping, this would simply be buffered, and then when we got back down into an acceptable area, it's going to be sent. So different ways to do these priorities. These are where some of the codes, and what some of the codes look like for these things. The 802.1p class, this is the layer 2. This is the VLAN tag, what's going to be in it. We got the tag, protocol identifier, and then the PCP, the priority code point goes in here is 3 bits, and the priority code points are down at the bottom. 3 bits means we can have 0 through 7. We can have 8 different ones of 8 different classification. So PCP, we got the lowest. The default is going to be 0, 0 the lowest, 1's the default, 2, 3, 4, 5, 6, 7 is the highest. And the acronym over here, and then what happens to this. Video is going to be a 4, voice is going to be a 5, internetwork control is going to be a 6, and then network control is going to be a 7. So what kind of priority are these different data is going to get? And then when we looked at the one in Wireshark, it had some of these strange numbers, and this has got arrows all over the place. But where we put this in the differentiated services code point, the DSCP, that portion of the IP header, you're going to get a code. You don't need to know these codes. You just need to know that you get a code in there. And the code is going to tell the system what kind of data it is, and it's from there it's going to get a priority. And then the network control there at the top, internet work control, the same order I think that we had going down. Voice over IP, broadcast video, multimedia conferencing, real-time interactive, streaming, signaling, transactional data on down until we get to our best effort at the very bottom of the queue. Industrial control systems monitor the industrial systems. They control the industrial systems. And there are two types of them, the SCADA and the DCS. The DCS is predominantly in refineries. The SCADA, large-scale distribution systems, they are, I think, fairly complex to operate, but the theory of them really isn't. They're going to control industrial processes. And I down here at the bottom said Stuxnet. Stuxnet was the attack against the Iranian centrifuges that they were working on for their nuclear material. And what this basically did was overspeed the centrifuges so that they would get burned up while sending a signal back to the control that said everything is normal. So there are network hacks available on these things, not just from the black hat hackers, but from countries also use these things. But what we have over here is the HMI, the human machine interface. Okay, we're going to be a computer here. Have you ever noticed that one of the things that runs on Windows is a human interface, and that's the mouse actually. Remote terminal unit, a PLC, a logic controller that goes here. This is going to be the device that actually changes what happens on the assembly line. It's going to turn them on, turn them off, do different things for it. So we have those things. And then the master terminal unit takes the commands and sends them to the remote terminal units to do those. What do they look like? This is what one. The upper left is what a board, a surveillance board of one might look like, and then over on the right is kind of a flow process. We have the SCADA, the standard interfaces, the data exchange center on down the line. The process or the flow, or I guess the logical process, is not really that big. But when you look at the things that you have to do, or you're actually controlling, or that you have to watch, it gets to be a pretty big system. And again, the SCADA is large-scale distributions, and then the DCS is for refineries predominantly. SCADA, and I can never remember, supervisory control and data acquisition, and maybe you can, but we have the computer center here, and over here on the right, level 4, the production and scheduling, the coordinating computer, production control, supervisory, the plant supervisory, and then the direct control goes to the field level, which go to the plant, which go to the devices themselves. So a large-scale control of industrial processes that go on with these things. The next topic, which I think thought was moderately support, is the Internet of Things, and the things that we put on the network connectivity, the data analytics, the things that we put on these things. We have manufacturing, healthcare, and we've talked about some of these before. Utilities, heavy machinery. Utilities have become an issue, and if you've seen some of the articles, there actually have been some compromises in some of the utilities around the country. Nobody's done any great damage yet. We know that there was one in California. It was in the middle of the night, and somebody tried to change the loads, but it didn't really affect anything because there wasn't a load. But the fact that it had been compromised is an issue. Over on the right, the home, we have the home automation, the appliances, the home monitoring, the different devices, some of which you may have or may not have. The phones will go down here, the communications that go on phones, wearables, TVs, all of these things, part of the Internet of Things that we are we have connectivity for all of these different kinds of devices. So the cameras, the Internet of Things, cameras, baby monitors, security systems, smart home systems, inventory management systems, wearable devices, connected cars, medical devices. I told you about my neighbor who had a heart attack and they monitor him constantly. Industrial applications, smart cities, all of these things. Smart cities, hopefully they'll fix the traffic lights so that they can be a little bit smarter with those things too. So we have all of those things. The next topic is network storage. I guess it doesn't really go all that far, but we have three types of storage. DES is directly attached storage. That's the hard drive that's connected to your computer. And then NAS, network attached storage. This is storage that's going to be attached to the network. It's going to have its own operating system. And after that, the SAN, the storage area network. And the one on the right, these show it too, but I think this one's a little clearer about where the file system goes in. The application software communicates with the file system, which is part of the operating system. And then it controls the storage and the direct attached, the hard drive that's on your computer. The network attached, we have an application software, goes across the network, and then we have this device that's attached to the network. It has its own separate file system. The SAN, the storage area network, the application software, and then we have the file system, and then after that it says FC, which is fiber channel or gigabit Ethernet that gets there. And that's the one that I want to try to show you what it does. And what I have, we'll use a couple of different technologies here, I hope. I'm using a remote desktop to go to a machine, and then we're going to have a virtual machine running here. In the virtual machine, as long as I can get onto it, I have this thing called a target. I have a storage server here, and this is just running on this device. Okay, so we will allow that. And inside of it, I have created this thing known as a target. A target's a disk drive. So I have created a virtual disk drive to do these things. So the target that we have on this particular machine, and I have the iSCSI targets, and I called it Net Plus Demo. And this is where it is in C:/demostorage.img. It's an IMG file, a virtual hard drive. But a virtual hard drive is going to take up actual real resources on this device. So we've created a hard drive on this server. Now it's a virtual machine that happens to be running on the machine that I created, what's called the iSCSI. We have the target initiator. I have to just find it. The iSCSI initiator, and it's connected here to the Net Plus. And we discovered things. I have the Net Plus. I have the IP address of this thing because it couldn't resolve the name. Favorite targets, I only have the one. The volumes and devices, and it's got a really long name. And this is what the name of this thing is going to be. And if I had authentication, I could have a Radius server connected up here. And then we do the configuration. After I connected it, the target, because I have the target, and this was the target that we created over there onto the server. After I created the target, I now had to go into my computer here, into the computer management, and I'll just quickly, hopefully quickly do this, and I go to disk management. And when it started up, this new volume down here, G, and I made it 100 meg so that I didn't want taking up a lot of room on this other side, was nothing there. I created a disk here on it, and it becomes the G drive. So now I can go to this PC, and I have a G drive. Nothing's happened to it here, but it's empty. But this is actually running on a storage area network that's on a server someplace else, going across the network using a protocol called iSCSI. And we can also use a fiber channel. I don't have fiber channel. Fiber channel is actually the preferred way to do these things. But this thing, we have the different elements that are required for this thing, for the storage area network, the application software, the file system on the machine itself, the fiber channel, and in my case, iSCSI that got to the storage, which was running on a system farther away from it. So the different elements of these, and this is just a kind of a bullet by bullet, the directly attached storage, usually a disk or a tape, directly attached by a cable to the computer processor, hard drive inside a PC. I/O requests are also called protocols or commands, and it accesses the devices directly. NAS, network attached storage. A NAS device, an appliance, usually an integrated processor, plus a disk storage is attached to a TCP/IP based network. It has its own operating system. Are translated by the internal processor to the device request when we do those things. A storage area network, storage resides on a dedicated network. And on these things, we really do need to put the storage area network on its own network, because there's going to be a lot of traffic that goes back and forth with it. We don't want it to interfere with the data traffic that we have. So we have those I/O requests. I/O requests access devices directly, uses fiber channel media, also iSCSI, and Ethernet media using an I/O protocol called iSCSI. Is emerging, and it has emerged. It's been around for quite some time. The definitions, the key definitions for these things, we have the host bus adapter, the target, the computer. A computer is an initiator, and the data storage device is the target and the initiator, the servers that connect to the shared storage device. So the target is what we're connecting to. The initiator starts the connection process to do these things. So I have, and it is 8 o'clock. Let's go ahead and take a break. Let's come back at 1:15, unless you got any questions. Let's go ahead and finish this one. So the host bus adapter is a hardware device. Could be a NIC. Something a circuit card provides I/O processing, and the one that I showed you, the host bus adapter, was a NIC. The target is the computer that is going to store, the device is going to store the data, and then the initiator is going to initiate contact with the target, with the storage device itself. The initiator piece of software, target's a piece of software. That I downloaded a piece of software as a demo to create the target. Microsoft, the Windows machines, the workstations, are going to have the initiators that be able to connect to it. The target's the issue. The new servers have the targets as part of them. That didn't used to be the case. What we may want to do here is jumbo frames. We may want to create frames that are greater than 1,500 bytes so that we can send more data at a time with these things. So jumbo frames, and if you do that, you've got to enable jumbo frames all the way down the line. On the NICs, on the switches, we have to allow that to happen. And then network attached storage, self-contained storage appliance. It is a device that has its own operating system and a hard drive. It's not going to run programs for us, not going to be able to do gaming on it or anything like that. But it does have an operating system that is specifically designed to do storage, and it is attached to the network. And you can use permissions on these things typically also. So storage area networks, this is going to be we're going to not have This would be the computer, the hard drive direct attached. This is not what we're going to have. We're going to have an array here, and this shows that the computers, we're going to do a load balancing with this, with a number of computers, going back through maybe a fiber switch or something like that to a disk array that's behind here. And these guys are going to control access to the disk. We're going to create virtual hard drives on the physical hard drives, and then we'll connect with the initiator through the target to the virtual hard drive. That's there. That will allow us to have storage. And we're going to have, in this one, showing two different networks. We've got the production network over here and the storage area network. They should be separated. We used to run ours on totally separate channels. We didn't. It was like this. We had separate switches for them, separate NICs in the servers, so that we could have them have their own network, and it didn't interfere with the data network. For one thing, you don't want people intercepting the data. For the second, you don't want to overload the data network with the amount of traffic that goes on. This is put in just to see what it looks like. I talked about iSCSI. The technologies are fiber channel, iSCSI, Internet, IP, SCSI, Small Computer Systems Interface, which has been a hard drive controller that servers use predominantly for years. FCOE, fiber channel over Ethernet, and then InfiniBand, the different SAN technologies. Up at the top here, on the iSCSI frame, we have the Ethernet header, no surprise there, IP, TCP, and inside here we have SCSI and then the data and the cyclical redundancy check at the end. TCP and iSCSI require CPU processing. They're going to require resources from the machine. Fiber channel over Ethernet, fiber frames encapsulated in layer 2 Ethernet frames, designed to utilize a lossless Ethernet environment. Large size, no TCP, so a lossless environment is required. No TCP, no resends, and no IP routing for these things. These are fiber channels, tend to be very expensive. iSCSI, not so much. You can set it up with a big hard drive, and what you're doing is creating storage for individual locations on the physical, breaking the physical hard drive, large hard drive, up into multiple virtual drives that appear as physical drives to the devices themselves so that they can store information on them. This is just more SAN architecture, some more images of this thing. The target, the shared storage, NTFS, whatever file system we're using, the SAN here, the storage area network. And then we have initiators, and this is showing that we can have initiators on any of the major operating systems, be it Windows, Linux, or Apple for Macs. For these things, the different protocols that would be used for these, at the heart of each of these, though, you see, is going to be Ethernet to do these things. And the terms here, I already did those terms, and I've had them up front. Let's just do it. Let's just make that slide go away. We don't need that one again. So fiber channel, we have a fiber channel SAN here, a host bus adapter, and then a storage array back here. So the host bus adapter, the HBAs connect to the fiber switch, is what this is. The fiber channel SAN switch. We have an HBA on the other side, a NIC at both ends of these things, and we connect to them. So the storage area network, these guys, we're going to have the completion, the installation, creation of the targets, and the targets are going to be the virtual hard drives. We have multiple connections here. This is for redundancy to do these things. iSCSI, we have a NIC that connects to a switch. A NIC over here, and the switch, and then connects through the switch to the storage device. These guys are going to have the targets, the software targets running on them, and they're going to create storage areas within the drive areas themselves. Table here about some of the what goes on with these things. iSCSI is the least expensive fiber channel. More expensive fiber channel over the Ethernet, a little less, and then InfiniBand is the most expensive. Which protocol are we going to use? SCSI, no specialized hardware. Fiber channel, specialized hardware. Over Ethernet, no specialized hardware, but specialized knowledge, hardware and knowledge for the InfiniBand. iSCSI, we're limited to Ethernet speeds. Fiber channels faster. Over Ethernet to the Ethernet speeds, and then faster for the InfiniBand. So the fiber channel itself, not over Ethernet, and the InfiniBand are going to be faster. iSCSI, longer distances. Fiber channel, but latency. A fiber channel up to 10 kilometers. Over Ethernet, longer distances, but again, latency. InfiniBand, short distances, less than 300 meters with it. So a trade-off on cost, latency, and range or distance that these things can be connected with. This is just another summary slide. Network attached storage versus storage area network. The top line is kind of significant. What kind of updates are we going to have to do with these things? The NAS, the network attached storage, is file level. If we make a change, it's got to replace the entire file. Whereas the storage area network's block level, we only have to replace the changes in the data in order to do that. And the primary media for each of Ethernet, fiber, the protocol, network file system, the SAN, SCSI, the one that I showed you was a storage area network. NAS appears to the OS as a shared folder, and the SAN appears to the OS as attached storage. And I always like to say on the storage area network, it's attached via the NIC, via the network cable. And it does appear, and it shows up as a local drive. Inexpensive, expensive for these things, dependent on the LAN, independent of the LAN. Architectural changes or no architectural changes. The reason the SAN needs architectural changes is it needs to be in its own area, so that we don't have the data traffic on the storage traffic on the data network to interfere with it. So we have some virtual and cloud systems. Before we do that, let me look at some of this. Is a virtual system here. This is, let's see if I can get that out of the way. I guess it's not going to go. Yeah, it is. What I want to show is what we can configure on this thing. What happens in a virtual system? I can have multiple operating systems. This is a Linux machine. It's not running right now, but it could be run if I had enough resources. I don't have enough memory to run everything at the same time in this machine. A Windows server here. When I go into the VM in the settings, what can I control on this thing? How much memory does it get? I've allotted it 4 gig, which was having trouble with it today, and I upped it. It'd been running with 2 gig, no problem. How many processors? It's sharing the physical processors. It's sharing the physical memory that's on the machine. Hard disk, 40 gig here with it. The hard disk, the SCSI hard drive. A CD is an auto detect. This would actually share the physical CD of the physical device itself. It would be used. What kind of a network adapter do I have? I can have over here 3 types. I can NAT it. I can have a network address translation where we use the address of the physical NIC to NAT. I can have a host only, which is going to be an isolated network. It's not going to go anywhere. It's going to go only on this computer and on the network that's created on this computer. And we could communicate with other physical machines or other virtual machines that are in host only that are in that network. The custom here, or the bridged. And the bridges is what I like. Bridged bridges the network. It gets its own IP address. I don't have to worry about NAT. The reason I like that, if I want to do a remote desktop to it, then I can do that. The USB controller, if I plug a USB, it's present. If I plug USB 2, and I think that, no, it's got a USB 3 also on that one. So whichever one that I want to use, no, it doesn't. USB 2, it can use the USB controller on this thing. Sound card is auto detect, and typically sound does not work all that well. Computer or printer is present, and then the display is auto detect on these things. So what we can configure on the device itself, and what all of these elements, these virtual elements of the computer do, is share the physical elements that are on the computer itself. So a virtual machine is simply a device that runs on another device, I guess, is for lack of a better sort of an explanation. And what we can do, we can have multiple operating systems. They work very well doing that. We share the hardware of the physical machine. The software is called a hypervisor. So this is VMware Workstation, and it is a hypervisor. There are other hypervisors that are a lot more sophisticated than this, but for running at home, this one is perfectly fine. If you want to play with Linux, go put yourself a Linux machine on. See if it'll actually start here. And it has. This is actually one that's designed to run with GNS3. It may not have enough resources because I put an awful lot of resource on the other machine. Yeah, there it goes. It's starting up. So I can have two different operating systems. I have a Linux operating system and a Windows operating system. That allows me to do things, to learn things about it without actually damaging my my computer, my machine. So we looked at the VM settings. We can edit the tab, edit. That's what I wanted. The preferences, and this is the preference of the entire workspace. Where we're going to store the virtual machines. The input, grab the keyboard mouse. So it's going to use the keyboard mouse. It's going to use the mouse that is on the machine itself. What hotkeys are we going to use? The display is going to auto fit. The window auto fit the guest. The Unity patches. What are we going to do with these things? Check for product updates on start. We can configure all of those things. The memory is the base memory. How much host RAM should the system be able to reserve for all running machines? And this says 4068, which is going to leave it not a whole lot. But when I'm running virtual machines, I'm not doing anything else on that machine. And then the devices that are disable auto run on all these things. So we can configure these virtual machines in order to run physical hardware, I guess physical hardware, run the operating systems, and the programs within it. So cloud devices and virtual networks. The virtual networks just simply mean the virtual devices. When I have a virtual NIC, you saw that I had a NIC there that shared the NIC on my device. So it is the virtual NIC when we do those things. The issue might be, and we had a server, big server, had I don't know 128 gig of RAM or something like that, and 8 processors, goes on and on. We would have one NIC. We had, I think, 95 servers running on it at one time. We weren't doing a whole lot with them, but we were running them just to see how many we could get started. But if we had a lot of traffic, we're going to overload the NIC. So you have to be careful about how you assign the information. That's one of the things that is an issue. Hard drive utilization is pretty poor. The memory utilization, we get somewhere around 90% efficiency. The processor efficiency, somewhere around 90% efficiency. Hard drive, somewhere around 60% efficiency. So if you've got a lot of hard drive activity going on, it can become an issue with them. So we'll look at these things, the cloud services. There's lots of virtualization, and we've talked about some of them already. We did VLANs with the switches, and it was just a matter of going in and creating the VLAN and saying, hey, port whatever, you're on this VLAN. Port next, you're on the other VLAN. A VPN, a virtual private network, an encrypted connection across an unsecure network. A storage area network that we looked at used the virtual hard drives. I know I didn't go into a great depth with it, but tried to show you the basics, the outline of what happens on this thing. So we have a storage area network is a virtualization that takes place. Lots of virtualization goes around in our networking. The virtual machines themselves, hardware, it gets cheaper and cheaper and cheaper and more powerful. And if you look at your computer, it's probably running most of the time somewhere around 3, 4, or 5% processor utilization. And it's probably, with the amount of memory, depending on what you're doing, maybe up to 20% memory utilization. What we can do in order to leverage the faster hardware is to run these virtual machines. We used to do that. We had a bunch of really, really old desktops. So what we did was take those really, really old desktops and some servers that had a pretty good amount of memory, processor, and storage on them, and we created virtual machines inside of it. So we had a bunch of virtual machines, and then we had our really weak physical machines out here. When they booted up, they started a really small Linux kernel, and Linux ran really well on them. And then after that, they started a remote desktop, which is what I was using to show you the thing before. I'm remote desktoped into a machine that's sitting on the floor behind me that's running. And it would connect to one of these guys, one of the virtual machines. Log on to the virtual machine with a remote desktop. Looks just like I'm on it. So these really, really weak machines that wouldn't even run XP are now running, at the time, Windows 7, and in some cases Windows 10, because all the processing is taking place on the server, not on the device itself. The only thing it's sending is keyboard and mouse commands back and forth. The processing takes place here. Powerful machine, has everybody got processor demands at the same time? In most cases, no. Does everybody have memory demands at the same time? That's one that maybe yes, but memory is a whole lot easier to add than maybe processing power. So we take this powerful machine and run multiples, and I think we were running probably somewhere around 20 desktops on the server. What's the downside? Server crashes, all your desktops go down. You have a connectivity problem because we got to have a connectivity to these things. We got to go through a TCP/IP network, busy network, or whole of our desktops may go down. So there are advantages and disadvantages to virtualization. Resources underutilized, and I guess that's what that whole little episode was about, that we underutilize the resources. Really, really powerful servers that sit around using 10% of their memory and 2% of their processing power. Why not leverage them and use what's available to us? The hypervisors, I said that the VMware workstation that you saw was a hypervisor, and it is a hypervisor. That's the software that runs these. We have two types of hypervisor. One is that one which runs on top of an operating system. It's running in Windows. The other one is a Type 2. The Type 2 hypervisors run on what we call bare metal. They're the operating system on the computer itself, on the server itself. They're designed to run virtual machines. That's what they do. They don't run Office, Microsoft Office, and email and web browsers and things like that. They run virtual machines, and they manage virtual machines, the distribution of resources for the virtual machines. We can run the different operating systems, and that's what I was trying to show with that Linux machine and the Windows machine at the same time. They don't affect each other. What are some advantages? Easier to back up. These things are just files. So if I want to move it from one location to the other, I can copy it, I can cut and paste, I can copy it, I can back it up simply by storing the file. If I want to try things, I can take a snapshot of it. And the snapshot takes a picture, a snapshot, an image of a point in time. And I was trying to do something to a machine one time, upgrade it or change it or whatever else, and it wasn't working. So the light finally came on, cha-ching, I can do a snapshot instead of having to go back and reinstall a whole bunch of stuff. I can do a snapshot. And I try this. If it doesn't work, then I go back in time with that snapshot. And I can try something else. If that doesn't work, I can go back in time to that snapshot. So snapshots allow you to preserve the current state of the machine so you can go back to it. Easier backup, easy scaling, and the scaling is so easy that we wind up with a virtual explosion, I guess. That's not really the word, but we wind up with a whole lot more virtual machines than we really should have because it's easy. I need to do this. Well, let's just put another virtual machine. Let's just put another virtual machine. We keep doing that. They still have to be licensed for Office or Microsoft. You still have to license the machines, but some of the servers, depending on which server version you have, you get several free licenses, and the higher you go, the more expensive the server. Obviously, the more licenses that you get with these things. The definitions here: virtualization, the ability to install and run multiple operating systems simultaneously on a single physical machine. A hypervisor, a thin layer of software that resides between the operating system and the hardware, allows virtual machines to interact with the hardware, the physical hardware, without going through the host operating system. Also manages access to the CPU, storage, and RAM. So it's the thing that manages control of the physical resources. The virtual machine, a software implementation of a computer. And if you think about it, a computer, we have the hardware, but the machine itself is a software implementation. It's a piece of software that's running on the hardware for these things. Appears to be self-contained, autonomous system, and the virtual machines think that they have access to all of the resources on the physical machine. The virtual hard drive is a virtual disk, is a file that's created within the host operating system. The host operating system is the Windows machine that I'm running, is the host, whatever is hosting the things that are going on. This is an image. We have the App 1, the traditional model. We have the different applications going through the operating system, and then they get through the operating system controls access to the CPU, the storage, and the memory on the device, on the physical machine. Maybe the email, your word processor, your Zoom session, and I'll say a web browser, all going at the same time. The operating system is going to determine which one gets which priority and how much of each of the things in the computer that they need. And this shows that this is both for Windows, Linux, and Apple. They all do the same thing. And by the way, you can't virtualize Apple machines. They're very specific. Underutilized servers, yes, we have those. Is what I talked about. CPU, about 8, 9, 10%. 10% we go up to 11 on 1. RAM, maybe up to 20%. But that's an awful lot of unused resource. It's kind of like unused resource, and I say in a car, although we don't use the maximum. If we use the maximum in the car, we'd eventually, blow up the engine, I guess. But we'd also probably get a speeding ticket. These things, we can use them more. 9% CPU, that's probably you're idling at a stoplight to do that. We want to be able to better utilize the resources, because you know, we're paying for it, and we're paying for it to just sit there. So let's do these things. The hypervisor takes the different virtual operating systems, and it is between them and the hardware, and it controls these operating systems' access to the hardware. And you saw that in mine. I had, and I didn't try to regulate the CPU, but how much memory I could control, how much memory gets set aside for the hypervisor to use for that virtual machine. And then we have the applications here on the VMs themselves. They're going to be running app 1, 2, 3, and 4 are going to be running on the operating systems, and they get access to the resources. Virtualization overview here, the servers that we do that, and I think we're still saying that doing the same thing. The servers here, the hypervisor that goes from goes through the hypervisor to the hardware, controls access to the hardware. This is trying to show, or naming at least, the types of networks that we saw in the VMware workstation there. We have an isolated, which is on the computer itself. It doesn't go anywhere. If we had multiple machines running on the isolated network, they could communicate with each other, but they can't communicate off of the machine. NAT is just that. Network address translation translates using the address of the physical NIC, translates to an address that's going to be given to the virtual machine. Bridged just bridges the NIC and gets its own. It's not NATed. It gets its own address to do those things. So NAT connects to the physical machine, and then it gets NATed to an address on the network to do those things. So we have the isolated networks, the NAT networks, and then the bridged networks to do these things. The next topic, which is we'll say topic, is software-defined networking. I'm trying to see where I am here. And it is a system that we actually do centralized control of devices. And this is showing switches. And you've seen me occasionally bring a switch up, and you know that there's going to be a configuration that goes on it. So what the software-defined networking does is take what's called the control plane, the configurations themselves, and puts them on a controller machine. So instead of going to each machine and doing configurations, we make the configurations on the controller machine, and it sends the information to the physical devices. And the physical devices have just what's called a data plane, and the data plane is where all of the work is done in the software-defined networking. And the things that are we've seen some of these protocols, some of them we haven't. We saw spanning tree, LACP was the link aggregation control protocol. UDLD we've talked about. 802.1x we talked about. Routing protocols, the only one we really talked about was RIP, which is not in here. RIP, we talked about ARP. And then the storage protocols that might be available. The data plane, this is the information that is at the control plane. And it sends the information to the data plane to do things. The forwarding tables to do routing, and the MAC address tables in order to do the switching and send it to the MAC address. The layer 2 protocols are the control plane. The control protocols provide the information to produce the things to do the work. So what we're doing is taking them off of the device and putting them on a central machine. Kind of one of those things, and this is a form of virtualization. And this one is, what are the elements of cloud computing? And we've kind of gone away from, and it's a form of virtualization. Had a friend that worked for a company that did a lot of cloud computing, and they ran a lot of virtual servers. And behind all of their thousands of virtual servers, they had 93,000 physical servers to run those machines on. So we got to have, at some point, we got to have the physical devices. But cloud computing itself, on-demand self-service. What that means is that if I'm running a virtual machine in a cloud and all of a sudden I'm expecting a big order or a big production or a big something, I can get more resources. I can get more processor. I can get more storage. I can get more memory, whatever I need to it. Broad network access. How do we get to it? Through the internet. We can use a phone, we can use a tablet, we can use a computer, whatever is available in order to get to it. Resource pooling. You kind of saw that with the virtual machines that we looked at, that we had a resource pooling. We had a bunch of resources. They were all pooled together, and then we distributed them a little bit at a time. And part of the theory here is that everybody's not going to need everything at the same time. Rapid elasticity, the ability to add more resources, and then measured service, the ability to get a bill is what that really is. That the provider can tell us, bill us, measure what we've used. The things that are available on the cloud computing, the three different services that we have: software as a service, platform as a service, infrastructure as a service. Software as a service, you use Google Apps, do you use Gmail, do you use Outlook.com? All of those are software as a service. All we do is connect to it and use it. Probably we're going to say Zoom is software as a service because all we do is connect to it and use it. We don't have to do any configurations with it. Platform as a service, Force.com, Windows Azure, VMware, Foundry, different things there, Amazon, Elastic Beanstalk, and the one at the top. What do they use for? Application development and integration are typically what the platform is going to be. Platform is just that, it's a platform, a computer, basically, to do it. So, and the things up here, software as a service, we use it. Platform as a service, we build it. And infrastructure as a service, we move it. Cloud storage. Rackspace is one of the ones, and you can, if you're curious about what these guys do, go to rackspace.com, and that's where the guy that I was talking about worked, that had the 93,000 physical machines to run all of their servers on. But the different things, and this is as the Gartner Group sees it: Google Apps, Salesforce, the Google App Engine, Amazon, Elastic Beanstalk, VMware, Cloud Foundry, but platforms that we're going to build things on or build with. And a lot of times we say application development because it's going to be isolated, and if we make a mistake with an application development, it's not going to interfere with anything. Infrastructure as a service is the everything here, the network security, system management, scalability. And when you do cloud services and you sign up for a cloud service, how much do you want to buy? And you do your own. This software as a service, or the on-demand. The guy I was talking about worked at Rackspace, came in to do a demo for a class one time, and he went through the process. He logged into his account. Of course, he was there. He had an account, and he said, "Hey, I want a Linux machine with so much memory and so much disk space and whatever the processing power that we used." And 20 minutes later, he had his computer. It had been configured for him. So that's what we mean by on-demand, the ability to do those things. We have several cloud types. And this is, okay, just how much, and NIST is the National Institute of Standards. I think I finally got that one in my brain. But the public cloud, made available to the general public. The I guess issue, if there is any, with the public cloud is you don't know who you're on the cloud with. It could be anybody. It could be the church next door, or it could be the hacker next door. So we have the public cloud. The private cloud operated for an organization, and sometimes they're operated on premises for the organization. But your organization in a private cloud is going to be the only one that's on that cloud. A hybrid cloud, two or more clouds that interoperate. And the other one, and it's a fairly new one that's come into the definition, the community cloud, share organizations that share a common purpose. Maybe a bunch of Boy Scout troops or Boy Scout regions get together and have a community cloud, or Boy Scouts and Girl Scouts, because they would have Boys and Girls Club would all get together and be in a community cloud because they had a common interest supporting communities. Organizations that share purpose usually is what's going to be in a community cloud. And one other one, the virtual private cloud, that simulate the private cloud experience in a public cloud infrastructure. And that one is, and then one other, that one is the brand new. And when we started out, we had the public, the private, and the community. And now we keep, kind of adding different things to entice people, I guess, to use the cloud structure. Cloud security is something that can be an issue. There have been, and that's what a data center might look like, and those are racks of servers in there. There have been attacks. There have been virtual machine to virtual machine attacks, and that's why I said in the public cloud, you know who you're on it with, and that's something that you may be concerned with, maybe not. When you run these things with cloud security, all of the security, the firewall, the host firewall runs on the host, the antivirus software runs on the host. Everything that we run on our physical machines need to be run on the virtual machines because they're operating systems. They just happen to be sharing the hardware with other operating systems. The problem is that they're in close proximity. So there have been not as many as there used to be, and I think they probably have most of it cleared up, but not as many attacks, but there have been some. Using an off-premise cloud service, secure communications to and from the cloud. We're going to have encrypted connectivity. We're going to have connectivity, period, in order to do that. Using a cloud for sensitive information, giving a lot of control to another entity, because what you're doing is giving a lot of control, a lot of authority to somebody that you may or may not know, but to a third party, to a Rackspace, to an Amazon Web Services, because they're going to be the ones that are managing this thing for you. And you can buy as much management as you want. Some small business, mom and pop businesses, are actually going to this instead of trying to hire somebody to come in 3 times a week, and then when it breaks, they can't get a hold of them because they're working their other job, their higher priority jobs, to do these things. So when you do these, you can buy the entire network if you want to do that, or you can buy individual services. A lot of places. I think when my son was at college, they stopped using or running their own email services, and they switched all of them. They had a choice in Gmail and something else, and I don't remember what the other one was because he took Gmail to have the university mail instead of at virginia.edu. So we have those kinds of things in the cloud to do those. And then when you do that, who has control of what's going on? And then back to my question earlier, where's the data stored? Where is it actually? Attacks on the public cloud service can affect several or even all the customers at a time. What was it, 2 months ago, 2.5 months ago, Amazon Web Services? No, Google had some issues, and that took down a whole bunch of big organizations. Amazon's had some issues like that too. Took down parts of Twitter, parts of Facebook. These guys don't run their own servers typically. They're going to be in the cloud. So if the cloud fails, you can lose an awful lot of services, an awful lot of connectivity with these things. Different cloud services, varying privacy policies. That's one of the things that you need to be sure of before you contract one of these guys. What kind of privacy, what kind of protections can you expect for your data? And that's something that they're going to tell you, but you need to ask those things. And just some thoughts, and this is what this is some thoughts about what's going on. Is it an emerging technology? Yeah, but it's one that's pretty far through the emergence process. A lot of people are using clouds. Amazon Web Services, enormous. Microsoft, they're doing really, really well lately. They're like the second largest virtualization service after Amazon Web Services. Google does that. VMware does a lot of it. There are a number of big organizations that do those things. So I will do that. And Donald just said he sees that I'm recording. Is there something you keep posting? Yeah, I'll put the link in. I didn't do anything last night, but I will do that. I can't do it on the Net Plus or any of those things because I'll give it to you guys. We don't want it to be out in a place where it could be public to everybody. And when they go on YouTube, and they go on as not as private, but as whatever unlisted is. So that you actually have to have the link, and I'll give you a link to a playlist to do those things. Different cloud services, varying degrees of privacies for these things. So that would